Hello and welcome to Team 74's presentation. My name is Devesh and joining me are Ian, Zach, and Joey. And we will be presenting our findings regarding possible air quality improvements for countries such as Hong Kong that struggle with air pollution. Today we will discuss the team's general design philosophy and factors that were considered for optimizing a previous model, as well as demonstrating that representation and sharing the results that we've received. To recap the situation, the team was tasked in finding a model that would optimize a smog-free tower designed by the Dutch inventor Dan Rosengart. The given design consisted of a system of numerous metal plates which had a current applied to them to generate an electric field. This field helped clean the dirty air using electrostatic precipitation. An internal air and particle movement system would bring the pollutants to a temporary storage while the clean air would be directed out of the purifying system. To optimize the model, the following objectives were set. The team needed to understand the effectiveness of the technology in removing air pollutants, as well as potential problems regarding the scaling up of the system. In addition, sustainability issues, especially long-term, and solutions to those issues needed to be identified. Finally, the model needed to conform specifically to the Hong Kong area, so the design was adapted to that scenario.
A Cotter's table was utilized in order to determine the most sensitive factors in our model. The three variables we decided to use were the distance between the plates, the plate area, and the charge of the particles. After utilizing Cotter's method and the impact velocity of the particles onto the plate, we found that the distance between the plates and the charge of the particles were the most significant in determining this velocity. We then decided that due to this, the plate area would best be determined from other variables in our model, such as the airspeed and the time it would take to impact, simply because the area of the plate wouldn't have that big of an effect on the overall velocity and time.
In order to solve for the velocity and time that the particles would impact the plate, we create a MATLAB script that would effectively draw a graph for us to utilize. We used three different variables that we would change to get different outputs. And these were the airspeed of the horizontal air across the plate, the width of the plate, which was also the length as we determined our plates would be square, and the particle charge, which in this case we used the charge of a proton. Following those variables, we had constants that would be later used for the model. And then following this, we had our initial values. And these initial values were just the initial state that the particles would be in upon entering the system. In this initial values area, we also have our delta t and delta x values. These would be used for incrementing in order to solve for the concentration and the velocity equations. Following those initial values, we have a while loop. And these while loops run while the particle is above the plate and the concentration is above zero. The concentration above zero was added because we found during testing that sometimes if incorrect values were inputted, the concentration would be going negative, and this is due to how we solved for the concentration changing. Within this while loop, we made two matrices. The first matrix being a velocity matrix, where we appended to the end the velocity that the particle would be going after every delta t. And then the times matrix that we created simply had the time that is passed in every index. This velocity value is just the last velocity in the matrix. And the recent velocity is the integral of the velocities matrix with respect to the delta t. And the distance from plate would be the distance above the plate that the particle is at any given time. And the distance traveled is how far horizontally the particle has traveled since beginning. We then found that if the distance traveled was greater than every delta x, we would increment I by 1. What this I did was change the concentration formula that we created. We found that the most simple way to solve for the concentration of particles above the plate would be to assume that they would decrease linearly as the particles crossed. So we assumed that for every 1% of the plate that the particle travels, the concentration would also drop 1%. So we used I to increase the amount that the concentration has decreased. And then following that, we have our increments where we increase the time temp, which is used for the distance traveled, and we increment the time by delta t. After this while loop, we then plot our times and velocity into a graph, which would look like this.
Moving on to the methods section of the poster. In order to optimize our smog-free tower, we created a model in MATLAB that featured several different equations, the longest of which being our velocity equation. This velocity equation was derived using Euler's method from a force equation that involved drag force, buoyancy force, and electrostatic force. To use the program, we were able to accept several inputs, such as the ones seen below in the recommended specifications section, that gave us the outputs seen in the same section. After doing this, we used Cotter's method to rank if each of those inputs was significant or not. And with the discussion section, we made sure to focus on the smog-free tower itself, as well as the factors that Hong Kong would kind of tie into it. So we thought about where the towers could go, how much smog is in the airspace of Hong Kong, things like that. Moving on to the recommended specifications section of the poster. Our inputs are seen on the left and the outputs are on the right. So the first input was airspeed, and this is how fast our fans on the inside of the smog-free tower are going to be blowing the air across each of the plates. So this is a horizontal velocity at a magnitude of 1.4 meters per second. Our distance between the plates, which is also the distance between all 36 levels of our tower, is 0.2 meters. The particle charge is 1.6 times 10 to the negative 19th coulombs. We got that number from the charge of a proton, and we decided on the charge of a proton because when the electrodes ionize the air, it knocks off one electron, which is equivalent to giving a positive charge of a proton. The width and length of the plate are both 0.28 meters because our plates are squares. So then we have the area of the plate down below as 0.0784 meters squared. And like I said earlier, we have 36 levels. So at 3 plates per level, we have a total of 108 plates. The height of our tower ended up being 7 meters based on our 36 levels and then 0.2 meter spacing between the levels. And the width of our tower is 1 meter, and it's a cylinder, so the width is actually the diameter of the circle. As far as outputs go, the average time for a particle to hit a plate at any given distance from a plate is 0.1 seconds. So that's not too bad. And then velocity impact was found to be negative 4.1794 meters per second. It's negative because the particle would be moving down. So the magnitude would just be 4.1794 meters per second. And our air volume per plate per hour is 282.24 meters cubed. So that's how much air each plate is able to handle per hour. And then the air volume per hour total, which would include all the plates, is 30,481.92 meters cubed. And looking at our number of towers, 4,600, that number is actually how many towers it would take to clean up all of Hong Kong's pollution, or PM 2.5, in one day. And that is assuming that Hong Kong is not generating any pollution at that time. So 4,600 is a fairly high number, and it's not totally feasible. And then below the recommended specifications section, we have our a short section of our Cotter's method. So factor 1 was the distance between the plates. We determined that to be significant. So changing the distance between plates heavily affected our velocities and other outputs. Plate area was not so significant. We were able to adjust the width and the length without it changing much. And charge of the particle, if we were able to charge it higher, it would have a greater impact on our velocities and other outputs. So we deemed that as significant.
After modeling our tower based on the original one, we had to consider the layout and population density of Hong Kong. Because the streets of Hong Kong are packed, the tower would need to be skinnier than the original tower. The team decided on a cylindrical tower with a diameter of 1 meter, skinny enough to be put on streets. The tower was made with replaceable yet high-quality parts, so in the unfortunate case that something were to break, proper maintenance could be done quickly so the tower could be up and running again. This includes having a stainless steel exterior as well as stainless steel plates. These towers needed to be able to clean more particles than Hong Kong's average daily emission in order to lower the total amount of pollutants in the air over time. From the EPA's recommendations, we decided to make it a goal to lower Hong Kong's air quality from a PM 2.5 concentration of 33.5 micrograms per cubic meter to under 10. With this in mind, we decided that such a drastic change in air quality would need at least 10 years to complete the process. With 4,600 towers scattered throughout the city, a place where pollutants and people are the most abundant, we estimated we would be able to reach this 10-year goal. The optimized tower design would cost $25,000 per tower and $115 million in total, not including the cost to power the towers after the first year. In order to clean Hong Kong in a day, about 40,600 towers would be needed, assuming there would be no newly admitted pollutants. Due to this cost and the large number of towers needed, these towers are not a feasible solution to Hong Kong's pollution problem. Hong Kong's dense layout would not allow for this great of a number of towers on the streets. Additionally, placing towers on top of buildings or places where humans are not around would not be optimal to help the health of the citizens. The towers would not be a long-term solution for the entire city, as it would be likely that more towers would need to be built and installed, costing the city more and more money. Hong Kong could implement stricter laws enforced on companies about how much pollution they can emit per year, making Hong Kong a safe place to live in terms of the citizens' health. Overall, because the tower was optimized for efficiency and the towers alone would not be enough to fix the pollution problem, we conclude that Hong Kong should implement the towers as a supplement to a more extensive solution.